Hi guys, it's George. Okay, so in this video what I'm going to be doing is going over some example calculations for some of the questions for the wind turbine lab. So let's go ahead and get started. So the first question I have here is, what is the total watt hours of power generated for the 24-hour period? Okay, so we have a formula for determining watt hours. So let me write that down here. So the formula is watt hours is equal to the power in watts times the time in hours. Okay, so this is what we're trying to find, and we need these two things multiplied together in order to get that. So let's go ahead and look at our data. So if you did the experiment, you should have something like this. You should have an Excel file that has a bunch of information. So on the left hand side, it'll tell you the time of day. So it's going to simulate 24 hours. And as you can see here, our highest power output was between 4 and 5 p.m. and that was 5.3 watts. This is not the number we're looking for though. We want to find out what is the average power output for this turbine. So in a given day, how much power on average should I expect out of this turbine? So the way we're going to do that is we're going to add up everything in this column. We're going to add up all the power output, and we're going to divide that by 24 hours. And that'll tell us our average power output in 24 hours. So let's go ahead and do that. Okay, so I already add them up and I got 8.04 watts. That's the total. And we're going to divide this by 24. So it can give us the average. So that's this guy, that's the power in watts. And we need to multiply this by our time in hours. And our time in hours is obviously 24 hours. Okay. And as you can see, this 24 cancels out with that 24, giving us a total of 8.04 watt hours. That's your answer right there. Okay, so let's go on to the next question. So the next question is, what would be the cost if sold at 10 cents per watt hour? Okay, so we have our output in watt hours. So we calculated that, and that was 8.04 watt hours. And it's being sold at 10 cents per watt hour. Okay, watt hour. Okay, so this one seems pretty straightforward. Let's just go ahead and multiply these two. So 8.04 watt hours. It's being sold at 0.1 watt hours, and this is money. Right, so here I would just move over a decimal point. So this equals 0.804 dollars. So that's how much it costs. Not very much, not even $1, about 80 cents. So this would be your answer. Okay, so let's go ahead and do another one. Let's do a fun one this time. So this time we're going to calculate the efficiency of our system. The efficiency. And the efficiency we're going to calculate using this formula, which is the work actual over the work maximum. Okay, so what this is saying is how much power or how much work am I getting out of my system compared to how much work I should theoretically get out of my system if there were no losses or anything like that. So let me just rewrite this really quick. So work of our turbine actual. I'm doing this because we're working with a turbine. So work of our turbine at its theoretical maximum. This is what we need to get. Okay, so if we look at our data over here, we can see that between 4 and 5 p.m., that is when we had our highest output. And this is the number we're going to use. We want to look at the system when it's theoretically working at its maximum, right? So, for example, we don't want to look between 8 and 9 p.m. because there was absolutely no wind here, and this tells us absolutely nothing about our system. But here was our most productive hour, so that's the hour we're going to use to determine our work of that our turbine is actually producing. So work of our turbine, actual is equal to 5.3 watts. Okay, so we have this one. We need to get this. In order to do that, we are going to use fluid mechanics. So let me go ahead and write down the energy equation. So the energy equation is kind of long, but it is mass flow rate times pressure 1 over density 1 plus velocity 1 squared on 2 plus the gravitational constant times the elevation 1 plus work of any pumps in the system. And this is supposed to equal mass flow rate times pressure 2 on density 2 plus velocity 2 squared on 2 plus the gravitational constant times elevation 2 plus work of our turbine plus any losses that might be in the system. Okay, so this is the energy equation, and it looks very complicated right now, but we're going to simplify it by taking out anything that we don't have in our system. So for example, there's no pressure in our system that we need to account for. So I can cancel out that guy, and I can cancel out that guy. Okay, so remember that what this equation is saying is that here something is going on that's affecting my system, and on this side it should equal whatever's happening on this side. So here we could say this is our fluid flowing, and over here it's going to be the output of our turbine. Just keep that in mind. So there's no pressure, we can cancel that out. There's no significant elevation difference here, so I'm going to take that out. Okay. Now on the left side, this is where we're illustrating our fluid moving, and our fluid is moving with some velocity. So this guy's going to stay. But as far as I can see, I don't see any pumps in my system, so I'm going to take that out. And on the right-hand side, there's no fluid moving, so I'm going to get rid of that. This whole thing just goes to 0. And since we're going to look for our theoretical maximum, we are not going to consider any losses at all in our system. So this guy also goes to 0. So what we're left with is that mass flow rate times velocity 1 squared on 2 is equal to our work of our turbine. Now this looks a lot simpler, and this makes sense. We have some fluid flowing with at some velocity with some mass flow rate, and that's the only thing that's happening in my system. That's going to turn a shaft, and it's going to give me my work of our turbine. That makes perfect sense. Okay, so now let's look what we're missing here. Here I have, what do I have? I have velocity 1. So velocity 1 is equal to this velocity right here, which is the speed that the wind was going at my most productive hour, which is 4 meters per second. So I'm going to write that down. 4 meters per second. Okay, what else do I have? I'm looking for this. I have this, which means I need mass flow rate. I need a way to get mass flow rate. So let's write that down. Mass flow rate. And the way I'm going to get mass flow rate is to use this equation from, if you remember from fluid mechanics, which is mass flow rate equals rho AV. Okay? And what this is saying is that mass flow rate is equal to the density of my fluid times the cross-sectional area which that fluid is going through times the velocity of that fluid. So let's see what we have. Density, have it here at 1.225 kilograms per meter cubed. Our cross-sectional area, we know the diameter of our turbine. It is at 3 feet. So diameter equals 3 feet, which when you convert it is about 0.914 meters. Okay? And since I have the diameter, I can use area equals pi r squared to get my area. I'll do that in a second. And our velocity, the velocity would be the velocity that my fluid is flowing at. So velocity would be 4 meters per second. Okay, so let me go ahead and get some more room. Okay, so we had mass flow rate equals rho AV. We have velocity equals 4 meters per second. We have density equals 1.225 kilograms per meter cubed. And I'm going to calculate my area using my diameter, which is 0.914 meters. Okay, so my area is going to be pi r squared, which is equal to pi times 0.914 meters onto squared. And this gives me 0.656. The meters get squared, so this would be meters squared, which are the units for area, so this makes perfect sense. Okay, so I have velocity, that's done. I have my cross-sectional area, that's right here, and I have my density. Okay, so I have everything I need now to calculate my mass flow rate. So let's go ahead and do that. All right, so this would be 1.225 kilograms per meter cubed times our area, which is 0.656 meters squared. And our velocity is 4 meters per second. Okay, so let's go ahead and fix the units first. So this guy cancels out 2 of those, so you're left with meters on the bottom. That meters on the top and cancels out with that one. So I'm going to leave you left with kilograms per second, which is perfect. That's exactly what mass flow rate is. So if I look here, I have this equals 3.2144, and our units are kilograms per second. That makes sense. All right. So now we can plug this into this equation, which is work of our turbine, theoretically maximum, is equal to mass flow rate times velocity 1 squared on 2. And this is 3.2144. And this is kilograms per second. And I'm going to have velocity 1, which is 4 meters per second. That's going to be squared divided by 2. And let's just check our units first. This is work, which means I must be left with watts at the end. Watts is the same thing as a joule per second. And a joule is kilogram times meter squared per second squared. So kilogram, meter squared, second squared, that's a joule divided by seconds. Yeah, that's watts. That looks right to me. Okay, so this I calculated as 25.715 watts. That is our work of our turbine at its theoretical maximum. So we're almost done. So let me clear this. All right, so we have the work of our turbine actual, which was 5.3 watts. We got that from our data. We calculated the work of our turbine at its theoretical maximum, and that we just got 25.715 watts. And now we're going to plug everything into this equation, which is work of our turbine actual over work of our turbine max. And this is 5.3 watts divided by 25.715 watts. Watts cancels with watts, which is right, because efficiency is a unitless quantity, so I should get just a number. And when you calculate it, you get around 0.2, which is roughly 20%. That is the efficiency of my turbine. Great. Okay. So now I just want to have a little discussion about what this number means. Okay, so we calculated how much power we should be getting out of our system, and it's right here. It's 25.715 watts. That's what the theory says. But in reality, when we actually use the system, we're only getting 5.3 watts. And this is due to irreversibilities in the system. Those are the losses that I took out of my equation at the beginning. That's what's causing my system to lose 80% of its efficiency. And this is one of the biggest problems with wind energy. It's just not efficient enough. This is one of the reasons why we don't use it. We should be getting a lot more, but with the technology we have right now, we're only able to get a small fraction of that. And that's why we don't use wind energy that much. All right, let's do one last one. So in this one, I want to estimate the power on land area required to provide power to my city of El Paso. So let's go ahead and do that. So let's see what information I have here. So I have that El Paso requires 350,000 megawatt hours per month. And let's see what information I have on wind farms. So in a wind farm, you can create about 1.2 kilowatt hours per meter squared per day. Okay. So this is the information we have. We want to manipulate these units so that they have the same units. So let's go ahead and do that. So let's see. Start with this one first. So 350,000 megawatt hours per month. I'm going to change that to days. So I need 1 month here, 30 days here. This equals 11,666.67 megawatt hours per day. Okay. And I'm going to change this guy to megawatts. Let's go ahead and do that here. 1.2 kilowatt hours per meter squared per day. And I'm going to change this to megawatt hours, so I'm going to move the decimal point over 3 times. So 0.0012 megawatt hours per meter squared per day. And megawatt hour, day, meter squared is area. Okay, I think that's all I need. So our final answer is our area required to provide power to El Paso is 11,666.67 megawatt hour per day divided by 0.0012 megawatt hour per meter squared per day. That cancels with that. That cancels with that. And I'm left with 9 million? Oh, that's a weird looking 9. 9,722,225 meters squared. That's how much area would be required to power El Paso. And this is another reason why we don't use wind energy. It requires a very large amount of land, which we do not have for wind farms. But I think that's it. I think that's all I'm going to cover in this video, and I'll see you on the next one. Bye.